Today we're going to be addressing flip-flops. Flip-flops are extensions of latches. They are synchronous sequential logic, which means they have a clock that synchronizes the behavior of the flip-flop. So with a latch, say you have a D latch, D enable Q and Q prime. While the enable is high, Q is going to follow D. So that's why it's called a transparent latch as well. A flip-flop is similar to a latch, but it has a trigger to it where a clock transition will trigger the latch. So it happens at a discrete point in time. So a negative edge triggered D-type flip-flop is made up of two D latches and they are linked together with the D input going into the first and the clock going into the first enable and then going through an inverter and going to the second enable. And Q goes to D in the second flip-flop, and Q and Q prime are out. So what happens is, this is a negative negative edge triggered flip-flop. Negative edge triggered type D flip-flop. Okay. So what happens is, when the clock transition is high, transitions to high, this D goes to Q, but when the clock is high, the enable here is low, so it does not pass through the second latch. When the clock goes low, or hits the negative edge of the clock signal, it latches Q here on the first latch, and then makes that high here for the enable on the second latch, So Q will follow D, which is the last output of the Q of the first latch. So the state table looks a little bit different. A clock Q prime when the clock is 0, the output has no change. When the transition is high, it goes to high on the clock. Again, it doesn't matter what D is, there's no change.
So, could high be interchanged with 1?
I'm sorry?
Could high be interchanged with 1?
No, it's a transition to high. That's the symbol for the transition to high. Only for that discrete point in time, not the high state. It's the transition to high. When the clock is high, again, there's no change. When when the transition to low occurs, that's when Q becomes 0 and Q prime 1, or so there's no change when it's low. I mean, when the clock is low. There's no change when the clock goes high. While it's high, again, there's no change. When it transitions to low, that's when the 0 goes from the D to the Q, and the 1 goes from the D to the Q. So this is the negative edge trigger. Now both of these. Those are the negative edge trigger that transitions the Q to follow D. So when the clock looks like the clock signal looks like this, the edge here is the only time D will be stored on Q, and it will be held there regardless of what other state there is. Now there's also a positive edge trigger flip-flop, D-type flip-flop. The schematic for that is a little bit more complicated. I don't know if I'd be able to put it on the board and make it very neat. I will leave it to you to find that schematic. It is using 6 NAND gates, and just so you see it, that's what it looks like here. It's a little bit more complicated than it's effectively 3 SR latches connected a particular way. So I will leave that to you to investigate and research. You can probably find a diagram such as this one on Wikipedia or a variety of other websites. But in the end, your D flip-flop has a slightly different signal. Or symbol. For the negative edge trigger that I just showed you here, it has a 0 bubble, inverted bubble, here on the clock input. And for a positive edge trigger, it's just the D and I guess technically the Q prime has a bubble here too. Because it's an inverted output from Q. Yes, the Q is the output, and this is the complemented output. D flip-flops are useful little doodads for storing information. They're the easiest flip-flops. And from the D flip-flops, you create other kinds of flip-flops. I'll get the T flip-flop is called a T flip-flop because it toggles. It complements its previous state. The T flip-flop you take a D flip-flop get it right. And what happens here is on the clock signal coming in, if T is 1 and previously it was 0, T will be passed through because an XOR of 1 and 0 is 1. So pass through to Q. On the next signal, if T is 1, on the next clock signal, if T is 1, the 1 from here will be fed into the XOR. With the 1 from the T input, the output from the XOR gate will be 0. So 0 will go out. So when you have the T input high, it will toggle the Q output and the complement of it as well. Another way to do this with just one input is to feedback the inverted output into the input, and with each pulse of the T, which puts into the clock, D will be inverted from its previous state. Each pulse will change Q from either high to low or low to high, which has an interesting effect. If you have a clock signal coming into T, your output, and say this is a frequency F, your output signal will be F divided by 2. So you can use this as a clock divider. When you string them together, say you have 2 of these, and this would be F divided by 4. Because you're dividing it by 2 and then dividing that by 2. Each one will divide it by 2, so you can have clock dividers divide by 2, divide by 4, divide by 8, divide by 16, 32, 64, etc. You can also sample these outputs, and this would be bit 0, have this be bit 0, bit 1, bit 2, etc., etc. It would be a binary counter. Each clock pulse would be a each yeah, this it would oscillate between 1 and 0, and every other bit, every other clock cycle, this would oscillate from 1 to 0. So you have a binary counter. And if you have, I know this is kind of getting into computer organization, ECE 312, but you have a binary counter. If you know your clock's frequency, you can compare your binary output from your clock divider and say you have a 1 kilohertz frequency coming in. When the binary number gets up to 1,000, 1 second has passed. So you can make timers, programmable timers, using this type of circuitry. Quite handy little devices. Now I've been debating on whether or not to cover the next flip-flop, because to my knowledge nobody uses it much anymore, because the D flip-flop is just so much easier to use and is smaller on the on computer chips. The JK flip-flop has 2 inputs plus the clock. I forgot the T flip-flop. Block diagram, block symbol is T, CK, Q, Q prime. So that's the block symbol for the T flip-flop. The JK flip-flop it's just a little bit different. It's a D flip-flop. The D input And yeah, the K is inverted. And this is the clock. Now the JK flip-flop is a little bit more complicated, as you can see from the schematic. When, let me see the state diagram here. When J and K are both 0, there's no change. When J is 0 and K is 1, it's a reset. When J is 1 and K is 0 is a set where the Q is 1. And when J and K are both 1, it behaves like a T flip-flop. It complements the previous state. So the state table is let's see here. And it is a complement when the J and K inputs are both 1. But like I said, the JK flip-flop is a little bit more complicated and takes up more space on a computer chip die. So the flip-flop is not used very often anymore. They typically use the D flip-flop instead. But yeah. Well, let's see here. I'm not sure if there's anything else in. We'll get into the analysis of clocked sequential circuits next time, and we'll see how it goes from there. Just 2 more weeks of lectures, and then the Thanksgiving break, then finals week. Yay! But we're all looking forward to. Have a good day, all.